Hello and welcome to lesson 25 of this Introduction to Probability of Wolfram U. The topic for this lesson is the central limit theorem. Let's begin. The normal approximation to the binomial, seen in the last lesson, can be seen as a special case of the central limit theorem. The central limit theorem plays a central role in probability theory and helps to explain why normal distributions are assumed so often. Specifically in lesson 18, where you could assume normal with at least 30 samples, or when the distribution was bell-shaped. The central limit theorem is the result of the joint effort of many important mathematicians. Notably, the first version was proven by de Moivre for Bernoulli variables of p of 1/2, then generalized by Laplace, but not rigorously, to be finally rigorously proven by the Russian mathematician Lyapunov around 1902. You'll see the theorem as well as its implications and usage. So first, the theorem can be stated as a sum of n identically distributed random variables standardized with mean 0 and variance 1 will tend to the standard normal as n tends to infinity. In terms of the CDF, one can equivalently say the probability this standardized sum is less than or equal to a tends to the normal CDF as n tends to infinity. Notice the formula is very similar to the weak law of large numbers for its identically distributed random variables, and it also resembles the normal approximation to the binomial for its convergence to the normal. All this can, of course, be extended to the multidimensional central limit theorem for the multivariate case, where distributions tend to the multinormal. The fuzzy central limit theorem is an easy-to-understand implication of the central limit theorem, and it states that data of small, unrelated, and random effects is approximatively normal. Rigorous proofs of the central limit theorem are numerous but are all beyond the scope of this class. It's worth noting, though, that there are many proofs using all kinds of mathematical concepts like moments, cumulants, convolutions, characteristic functions, and more, as this theorem arises in all kinds of applied sciences in different ways. At the very least, the effects of this phenomena are easy to visualize, as any random distribution of means gets closer and closer to the normal distribution as the sample size is increased. The central limit theorem has a wide range of applications, depending on your need. With minimal data, you could estimate the mean of a population, as it's done in opinion polls. With more data, you could estimate a range of values for a desired metric with some degree of confidence, as it's done in risk analysis. With a lot of samples, you could estimate the entire true population distribution, as it's done in election polls. But these are general applications. In experimental science, for example, error is assumed to be normal, so hypothesis testing is often about finding the threshold around a normal expectation. In noise cancellation, normal noise is assumed when cleaning a signal. In modeling, non-normal behavior is often considered an indication of non-trivial behavior. For example, what's the probability the mean snowfall in Buffalo is greater than 77 inches for a sample of 50? Notice here the question is not about a single sample point, but the mean of 50 samples. So first, load the data, then find the probability x is greater than 77 inches, where x is normally distributed over the mean and the standard deviation, divided by the root of the number of samples. And there you go. Intuition may lead you to believe uniform randomness is more common, but normal randomness is always more common. as many common phenomena are the result of aggregation. Consider a walk of 25 steps where you either take a step up or down and you note each time your position. Okay, so yes, one possibility is that you choose always down and you end up with a uniform probability distribution. But consider most other paths, the great majority of which form a bell-shaped distribution naturally, and thus normal. So okay, sample distributions converge to normal distributions, but how fast is that convergence? The convergence of the central limit theorem is proven to be monotonic, non-decreasing, and uniform. The full understanding of this is left as an exercise. But what does this mean practically? It means that yes, a bigger n will always lead to a better approximation, assuming a lack of bias. But the rate of convergence is slow, meaning improving the accuracy of an approximation by a small margin is often very costly. For example, you want to measure a mitochondrion's length. Your instruments and methods have an error variance of 2 micrometers. How many measurements do you need to be 99% certain that your average length has at most half a micrometer of error? First, remind yourself of the central limit theorem. The probability you're searching for is the probability of your sample mean is at most 1/2 away from the population mean. To get from this to this, you need to multiply by the square root of n and divide by the standard deviation, leading to this, and so you can calculate it. So find the probability z is between those two bounds, where z is the standard normal. Then, since n is unknown, solve this for the probability is equal to 99%. And the result shows n must be greater than 53. So since measurements are discrete, you need to round up to 54 measurements. And so 54 measurements are needed. Now it's time to critically review the central limit theorem, starting with the pros. The central limit theorem encourages sampling distributions and poles in all their forms as inference is made easy and affordable. In fact, in many fields of science, unknown distributions is commonplace, increasing tremendously the applicability of this theorem. But let's not forget the cons. Like any approximation, the central limit theorem cannot provide absolute certainty, so it's always possible to make an error. If there are indications of non-normal behavior, it's usually preferable to use more precise distributions. Also, the central limit theorem assumes unbiased samples and has much greater error on biased samples. So to summarize, the central limit theorem states sample distributions are asymptotically equal to normal distributions. This theorem has many applications in different fields, but it's often misused as you need to make sure your application is appropriate. Asymptotic approximations should be used mindfully, considering the data type, bias, and size. This was the last lesson from this Introduction to Probability. From all the team here at Wolfram, we hope you had a lot of fun, and we wish you good luck and thank you.